Hi there. Today we'll look at SpineNet Learning Scale Permuted Backbone for Recognition and Localization by Xianze Du et al. Of Google Research. On a high level, this paper proposes to take current recognition and localization networks, which have a CNN backbone, usually something like a ResNet, and switch up the order of the blocks in the ResNet and cross-connect them in a different way, such that they reach a higher accuracy with the new network that has the same amount of parameters or almost the same amount of parameters. They then further modify this network such that it reaches that higher accuracy with less compute than the original network. So if you want to know how it's done, stick around. You can help me by sharing out this video if you liked it. If you didn't like it, leave a comment and tell me what you didn't like. Otherwise, I have no chance of improving. So that's the deal. Okay, cool. So the task here is recognition and localization, as you can see here, which basically means that you have an image and there's stuff on the image. Maybe there's a cat right here, and maybe there is some kind of a house right here. And these tasks come in various forms, but some of the tasks are to say what's on the image. So in this case, cat and house. And also, where is it? Now, this could be a point, this could be a bounding box, or this could actually be a pixel segmentation. All of this sort of tasks exists in various forms. What usually is done in these tasks is you want to go in some way through a neural network, and the neural network will output the same image again, or the same shape. So it will output an image that is of the same shape. That if this is your input image, I'm just gonna quickly redraw without the labels. If this is your input image, then the output image, let's say we're doing bounding boxes. The output would say something like, here are bounding boxes, and also the output would be cat and house. So these are the two outputs that the neural network would generate. This is some sort of a convolutional neural network because they deal with images fairly well. Now, usually when we do image processing, and we know this from, for example, image classification. So if we just have image classification just to classify here, if we just want the outputs cat or house, or even just one single thing like an ImageNet, our convolutional neural networks have a particular architecture. Namely, what we do is we have the first convolutional neural net, the first layers will take the image and run these convolutional filters across them, which gives you the same shape image back. But then with time, we scale it down. We have a max pooling or a convolution with stride 2, so that the image is only this big anymore. And then we have a bunch of further layers, and then we scale it down again, and so on. Now, as we scale it down, the number of channels goes up. Of course, at the beginning, you have 3 channels for the 3 colors. But then after the first convolution, you might have, 32 channels right here. This is no longer the original image. This now is, of course, for each pixel, you have a stack of features, right? You have a stack of features right here because that's what your convolutional layer does. And then when you scale it down, you have even more feature maps. So we tend to scale down the resolution of our feature maps, but we tend to increase the number of feature maps right here. The reasoning behind this is, if you look at these bounding boxes, they don't really, if you look at the labels right here, the fact that there's a cat on the image shouldn't depend on the exact pixel location of the cat, right? So even if I scale this down a bit, I'll still recognize that there's a cat somewhere. It can still aggregate that information. In fact, I could deal with a single, right? I could deal with scaling this down successively up to a single pixel. And that's ultimately what an image classifier does. You simply have a single vector at the end with the features in it, and from that you classify. So the reasoning is that as you go through the network, you pick up the low-level features first. Like here, you pick up the edges and the kind of low-level shapes. As you go higher through the network, your features become more abstract but less localized, which means that it's less important where they are. And that's why you look at this image through a coarser and coarser segmentation. And at the end, your segmentation might be something like this. Okay, so we have had a lot of success building image classifiers with this reasoning. And this is sort of a human heuristic that just has worked well, right? Now, when we do something like this, bounding box classification or even per pixel classification, all of a sudden, it is very important where the things are, right? It is very important that it's this pixel and this pixel and this pixel and this pixel forming the bounding box, because the more accurate you are, the better your bounding box classifier. You still have this right here, this recognition, but the localization part, we can't just scale down anymore because we need to output something that's of the same size. So what people have done is they've gone from this kind of, architecture that scales down, because we know that works well. We know the downscaling works well. So we take that and then we scale up again. And there is some reasoning behind this, right? So that's what we can do. Because we know this part works very well for extracting high-level features that are not that localized. So our reasoning is going to be something like, okay, we'll force the network through this kind of bottleneck right here. We'll force it to learn some high-level features. Because otherwise you can just, kind of remember the individual pixels, and that won't work as well. We'll force it to remember the high level. We'll force it to remember what a cat is. And then it will help in the pixel segmentation to know what a cat is. This is a very valid assumption, but it doesn't need to be the case. And so there's one additional thing that these networks usually do, is that they have like some skip connections here from the layers that are of the same size to the layers that are of the same size, right here to here, in order to kind of recover these high-level features. Because if you only look at an image through the lens of this right here, and you have to segment the ear of the cat, you can only either color an entire pixel or not. So you want to gain back some of those high-level features, and that's what you do with skip connections. And that's why these networks usually look like this. Now, in this work, the authors sort of criticize this. They say, why are we doing it like this? Isn't there a better way to do it? Specifically, we want to look at this part right here, which is called the backbone. So we assume that we have these output layers that give you at different scales different features, and what we have to do is we have to construct a backbone that somehow feeds features, either through this direct way or through these connections right here, feeds features to these ultimate classifiers. So these classifiers will then be used to classify the bounding boxes and classify the output classes for recognition and localization. This is an illustration of this. On the left, you see a typical backbone, and they call this a scale-decreased network. So an example of scale-decreased network on the left versus a scale-permuted network on the right. The width of the block indicates feature resolution, and the height indicates feature dimension. Dotted arrows represent connections from two blocks not plotted. Okay, so on the left you have the typical architecture. You see that the width, so this is the resolution, is very high, and as you go through the layers, that resolution gets smaller and smaller and smaller. But the number of features indicated by the height gets higher and higher and higher as you go through. This is your typical architecture. We are looking into, let's say, that this is not the only one. What we can do is we can build any sort of backbone. And here they restrict themselves. They say, okay, in order to make it comparable, in order to be, scientifically a bit more rigorous than just building anything, what we restrict ourselves are simply permutations of this. So we only allow us to permute these things. So all this goes here and this goes here, as you see, and that ensures that you still have roughly the same amount of parameters. Now there is a sort of a parameter difference because these connections here, you need to up and down sample the images, and sometimes that introduces parameters, but in essence you have the rough same amount of parameters, and then you can really research what can we improve a network simply by rearranging its blocks, because that would give evidence that this scaling down architecture isn't really the best one. Okay, so here you can see an example of this. This is what they call a scale permuted network. Sorry, this scale permuted network right here. So in a scale permuted network, what you're allowed to do is you have these blocks on the left, and you're allowed to put them anywhere you want in any sort of I don't want to say order, but yes, in any sort of order. Yes, it's an order actually. So it goes from here down. This is 1, 2, 3, 4, 5. For any block, you first place this block. You're allowed to connect it to any other block before it. Now here we don't see, but you can see there's 2 incoming connections right here. So we make use of more than one connection. On the left you see there's always one connection between the blocks, and on the right you see we allow up to 2 blocks to connect to a given block. Okay? Then you're done with this block, you place the next block, this one here. Also, you're allowed to have 2 incoming connections, this one here and this one here. And you place the next block and so on. Now, how you make these, you also see that there doesn't need to be like a straight linear path, because there is no connection right here, if you can see that. So you might be wondering, how do I decide which block goes where? And how do I decide on which connections connect where? And that is going to be the idea here, to use neural architecture search. So neural architecture search right now is still a fancy way of saying, let's try stuff out. And so what you'll do is you'll initialize a reinforcement learning controller that decides on the ordering and on the connections, and it has some action space, and you basically let it run. So it proposes a couple of architectures, and then you measure all of them, you train all of these architectures, and you see how well they fare, and then you go back to the controller, and that's the reward signal. And so we can draw, so you have an agent which builds the building plan. So the agent will emit as an action a building plan, like big, small, big, small, big, with connections like this and like this and like this. And then that will go to the environment. The environment here simply takes the architecture and train the architecture. And then let's say the eval loss, or the validation loss, the validation accuracy is going to be your reward signal. So you simply train a reinforcement learning agent to solve this particular problem, which is training this recognition and localization on a particular data set as well as possible, to basically come up with the best architecture, which, it's fancy and it's a bit better than trying everything out, but it's not much better right now. And it takes a lot of compute to run these experiments, because it takes a lot of iterations of this, and every iteration consists of training one of these networks fully once. Now you can do something with like early stopping and stuff, but so you get the idea. This is what they propose, and this is how they get better. So there are a number of challenges in this. Namely, we said, okay, when you input a signal, for example, when you input a signal from this layer to this layer, you can see that you have to shrink the resolution, and you have to up the number of features. And this was already sort of solved in the original ResNet paper, but they reiterate how they do this here. Basically, you have this layer, and it is connected to these 2 layers. We said every layer can receive inputs from 2 layers. You see at the very end, these are just added together. Okay? So we have 2 things. First of all, the number of features is different. You can see right over here, the number of features, the number of channels is different than the number of channels in the output image, let's say right here. So those are different, and in fact they're different in both inputs. And we have this method of one-by-one convolutions that was introduced in the original ResNet paper. If we do one-by-one convolutions, it's basically a learned transformation from a number of input channels to a number of output channels without doing any actual convolution operation. This is simply a linear operation, upscaling or upping the number of feature maps. You can see these one-by-one convolutions are employed here in various ways. So because this is fairly compute intensive, or so they claim, what they do first is they always first go to less features. So here we have a number of features, which is maybe, let's say this is this is C0. You can see very small here maybe that there is this, first we go to alpha times C0, and alpha is, I think in the default setting, it's 1/2. So first we always go to 1/2 the number of features before we do this switch here. And then we have two options. Either, so you go to 1/2 the features, and at the end you go to the number of target features. So it could be, if the target features are more than you currently have, it could be that you first go to less features and then you go to even more features, right? As if the current one has more features than the end, it's probably not as bad because you first go to less features and to even less features. This is probably one of the things they did to save computation, but which you can imagine that it hurts, because here you simply have to basically throw away half the features, or you have to like linearly combine them in every step where you connect two layers to each other. Okay. So there's two situations. First situation, your current resolution here is higher than the target resolution. In that case, we can simply do a convolution with a bigger stride than 1, right? If you have an image and you do a convolution, usually you have this overlapping convolution such that the result is the same size as you started with. But you can also do a bigger stride, and I'm a bit overdrawing this here. But you can do a bigger stride such that the final resolution is smaller. And you can also do this max pooling right here. So the max pooling is also a way to reduce the number of the resolution of the image. So if we're bigger, we can do that. If we are currently smaller than the target, what we can do is we can upsample. And upsample you can do by doing nearest neighbor or things like this. You can also do a learned upsample. There are various ways. I believe here they do a nearest neighbor, but I'm not sure anymore, actually. Let's check it out. That's here somewhere. Resampling and cross-scale connections. Yada, 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 yada. It's important to keep the computational resampling low. We introduce a scaling factor alpha. We had that. Then we use a nearest neighbor interpolation for upsampling, or a stride 2 3x3 convolution. Okay, so it's nearest neighbor by upsampling. All right, so that's how they up and down sample the feature maps to the correct shapes, either using nearest neighbor upsampling or using multi-stride convolution followed by max pooling. So what does that give them? Now, they do several different steps in this. So the first architecture, this ResNet 50, is the original architecture. And remember, we're only talking about the backbone right here. Now, in the original ResNet 50 architecture, you have this ResNet 50 FPN, and this FPN these are called the output layers. This is what then goes and classifies the bounding boxes and the labels and so on. Now, here you can see the ResNet 50 is continuously getting smaller and more features. They do an intermediate step. So this right here is their final thing, where they let this algorithm go wild, and you can see that it's pretty fuzzy. So this RL controller finds this architecture to be the best architecture, and you can see it's continuously down and up and down and sorry, and up and down, and there's considerable cross connections between all of these things. And then here you have the different output layers built into the network rather than next to the network, right? So these are the ones that are now, the red bordered ones are now the features that are used for going and classifying. As an intermediate step, they also consider this architecture, where they basically built a smaller ResNet right here, and then let the algorithm decide on the rest right here. So it still has the same amount of parameters, roughly, but they can investigate what happens if we go to this lower, if we have this structure at the beginning, but then part of it we can do with our algorithm. And lastly, they also consider this architecture. Now this architecture, again, their algorithm has control over the whole network, but there is an additional thing that the algorithm can do. The algorithm can also decide to change the number of features and to change the type of block. So here you can see these are all residual blocks, and these are called bottleneck blocks. They're simply a different way of doing a residual block. It was introduced in the original ResNet paper, but the controller can simply switch to that, and that can save some computation if you go through these bottleneck blocks. So what does that give you? You can see below that the ResNet 50 is at 37.8% average precision. If you liberate the top part to leave it to the algorithm, it's at 39. If you liberate the entire network, it's at 40.7. And remember, these are like roughly the same amount of parameters. And then if you also let the network control a bit of the feature size and the type of block, you get a 40.8, which is the same as before, but now this one, I believe, has about, oh yeah, here we go, with 10% fewer flops. Okay, so that's pretty cool. Though, remember that the left thing, this is made by humans. This is just our heuristic. And the right things, they are made by RL. And they are, for these particular data sets, though they do find that generally this also transfers to ImageNet classification, but still this is sort of it works well for the type of data we work with and so on. So I don't know how much I would trust it, how far we should go of building SpineNet 49 as our new backbone for every image task that we have. It remains to be seen, I believe. Before actually we go to the experiments, I want to state my idea right here. So you get the general gist here. And so another kind of quarrel I have with this is that, in here, you always have these single connections. And here you always have these double connections. And I've looked through the experiment. It seems like nowhere do they ablate or anything what it means to only have single connections, or if they let the ResNet run with double connections. So if their controller could not switch the order but only introduce the connections, they might have done this. They have a lot of experiments where they do the different ablations. So I would be interested what happens when you let it run on the ResNet but let it have two connections per layer. Is it then better or not? So here the importance, I'll get to my idea later. The importance of scale permutation, that's where they investigate how important is it that you permute the layers, and that turns out to be fairly important. Then the importance of cross-scale connections. That's how they investigate here. So these are these connections. They say The cross-scale connections play a crucial role in fusing features at different resolutions throughout the scale-permuted network. So that's the reasoning behind it. We take features from different kind of resolutions, and we can also scale up again and then scale down again to gain some additional features from the higher resolutions. We study its importance by graph damage. So either they remove the short-term connections, or they remove the long-range connections, or they remove both and then connect one block to the previous block via a sequential connection. So this is only in the things that they learned, right? So this model is where they fully give their model control over the ordering and connections. You can see that as this 40.7%. Now, if they delete the short-range connections, they drop to 35. If they delete only the long range, they drop to even more. So here you can see that these long range connections, which I guess are connections that are going across multiple blocks, skipping multiple blocks, these tend to be very important. So you can make the case that it might be very important to fuse these things from different layers, to fuse the features from different resolutions, because these long-range connections tend to be important. Though it's one thing to say that if we just leave them away with our model, if we just damage it and then let it run, it drops in accuracy. It's not entirely the same thing as to say that these are important, because you don't really know what happens like if you train without them. Maybe you could, if you train without them, you could reach as good an accuracy. So this graph damage investigation, it has something, but not, I wouldn't trust it too much. And yeah, I think they haven't investigated what happens if they keep the ResNet order but let the connections be twice. But you get the general idea of the paper right here, of what they do. Now, they do this with architecture search right here, but here's an idea, okay? I propose the following. You have an image right here, and we are wondering here, should we let it go through a layer that's wide and with less features? Should we let it go through a layer that's very many features but not as wide, but we have to downscale the image? Or should we let it go first through something intermediate? Let's see it like this. Okay, so we're wondering, how should we order these blocks? Why can't we do all of at the same time? Why can't we do this, this, and this? Okay, and then in the next layer, again, do all of them at the same time. And you can already see where this is going. I hope you can see where this is going. So you have a routing right here. And how do we do routing in modern times in deep learning? With attention. So I propose you have layers with different attention. Let's say these are now your sequences, or you can also make them as attention heads. Okay, these are these, and the lower level features are routed to the higher level features with an attention mechanism. And you do this layer by layer by layer. So because what's the problem here? The problem here is that the same data point has to go, you find these good connections, but all the data points have to go through the same connections. And it might actually be that you need different routing depending on the data point. It might be that this is good for the average data point, but it would be much better if whenever there's a cat, you take one path, and whenever there's a dog, you take a different path. So this will allow for that. You basically have the routing parameterized by an attention mechanism. I have no clue how much compute this would take. It doesn't seem that outrageous, because what's your sequence length here? Your sequence length is going to be the number of layers maybe, and maybe times the number of feature maps. Maybe you have different attention heads, so you maybe want to replicate some of those here. But ultimately, I would guess the attention mechanism itself isn't that much of an overhead. Maybe it's an overhead that you have so many in parallel Yeah, but you know, it remains to be seen. That's the idea. Yeah, you heard it here first. Okay, so they have more experiments. So they also build. Here is where they say, okay, we have this SpineNet 49 now, and we found this to work. We found this to work really well. This is our SpineNet 49 architecture. Cool. And we want to make it bigger. But I guess they didn't have the computational resources to run the neural architecture search for bigger networks. This is now about as big as a ResNet 50, right? But what if you were to go to a ResNet 100 or a ResNet 150? There you don't have the computational resources to do neural architectures. Imagine this, Google doesn't have the computational resources to do neural architecture search on this thing. So this must be expensive, or I have no idea. But what they do is they kind of do a trick. So here they take the SpineNet 49 and they say, we build a SpineNet 96 by simply repeating each block twice. So all the incoming connections would go to the first block, and all the outgoing connections would come from the second block, right? Here you had 2 in, and maybe there's actually no limit to how many outgoing connections you can have. And you can also do this 3 times, which I think is a bit of a cheap way, and it kind of defeats the entire purpose, right? Couldn't you make the exact same argument again here, that maybe it's helpful to route from this block right here, or maybe it's helpful that these don't have the same scale right after one another? It just seems, but okay, so they say we found this good structure and we simply duplicate each block. I'm not that big of a fan in any case. So they train this, and it of course outperforms everything else if you compare with kind of models of the same size. So here you compare this SpineNet 49 to the ResNet 50, and you can see there's about the same number of parameters, but it outperforms the ResNet 50 pretty much. And as you go up the number of parameters here, the performance goes up yet again. And I believe these dagger ones here are simply trained with a special schedule with, with applying stochastic depth and swish activation for a longer training schedule. So you can see that not only are these SpineNets, the number of parameters is here. Not only are the SpineNets slightly smaller than the ResNets, they do require less flops. And they reach better accuracy. So, you know, everything is a win here. Yeah. So they apply this to these data sets. I don't want to go, too much into that. But in the last part, they also apply this to ImageNet. So there's image classification, where they basically say, okay, we can just go to our architecture and we can just add up all the output blocks. We scale them appropriately and add up all the output blocks right here, because these are good features for localization and so on. And we can train it to do image classification. So all of these go into a big combination classifier that does the 1000 classes of ImageNet image classification. And that also works pretty well with this network. So they basically argue what they found is sort of a better image processing network than the ResNet 50. And I guess they would argue that from now on you should take this as your backbone for image classification and recognition and so on, which it's entirely possible that this works better. There's no particular reason why the ResNet 50 should work at all, right? It's just a heuristic. But I guess, it remains to be seen whether that's generally true or just in the things they considered. So you can see right here, the SpineNet generally improving over the ImageNet, which is not stated right here, but it does generally improve. And you can see as you go higher and higher SpineNet, the numbers tend to improve as well. And this is already pretty respectable number for ImageNet, right? All right, so this was it for this paper, for this particular paper. They do have, 2 different of these object detection recognition data sets, and I invite you to check out the experiments more closely if you're interested in that sort of thing. I was mainly interested in the method of doing and arranging these layers and so on. It seems like it's a cool engineering project, cool investigative project. The experiments are done well, and in the end they reach a better, they get a better model out of that. And if it turns out that this model is a good model, the entire community will be better off. Unfortunately, there's no broader impact statement to tell us that also the terrorists will be able to use this for purposes, but you can imagine that yourself. All right, that was it from me. Again, leave a comment if you want me to change anything or have suggestions. Leave a like if you like the video. Share it out. Bye-bye.